Today you are going to have a look at linking the roots of polynomials and its coefficients, and that goes beyond quadratics into cubics and quartics, and you're going to use substitutions to solve more complicated equations. Let's take a look at this example. The quadratic equation x squared takes 6x plus 18 equals 0 has roots alpha and beta. Write down the values of alpha beta and alpha beta. So if we take a look at the first part, so the sum of the roots alpha plus beta will be equal to minus b over a, and alpha beta, the product of the roots, will be equal to c over a, where a is the coefficient of x squared, b the coefficient of the x, and c is the last value. So if we work these out, so we have minus, and b is minus 6, and that's over 1, so that gives us 6. And for the second one, we have 18 over 1, which is just 18. Now part B, find a quadratic equation with integer coefficients which has roots alpha squared and beta squared. Now, the best thing for us to do there is a similar process to what we've just done above. So we're going to find the sum of these new roots and the product of these new roots. So alpha squared plus beta squared, we know is alpha plus beta all squared minus 2 alpha beta. And we know the values of these. This is 6 squared minus 2 lots of 18, and this will give us 0. And alpha squared beta squared is alpha beta all squared, which gives us 18 squared, which is 324. So if we put these into the function now, into the quadratic, so we have x squared minus the sum of the roots, which is 0, so we'd have 0x, plus the product of the roots, which is 324. So that gives us x squared plus 324. And then on to C. So now we're trying to find the values of alpha squared and beta squared. So we want to know what the roots are of the quadratic that we found in part B. Now we know that 324 is 18 squared. So if we factorise this, this gives us x plus 18i and x minus 18i. Just think about that. So that's 18i multiplied by minus 18i, which would give us 324. It would be minus 324 as we have the minus 18, but then we've got the I squared, which is also minus 1, so that gives us 324. And this means if we continue and solve this, so we are setting that equal to 0, that would give us x to be equal to plus or minus 18i. Let's take a look at this example. The quadratic equation 5x squared minus 7x plus 1 equals 0 has roots alpha and beta. So here, if we define a to be 5, b to be minus 7, and c to be 1, we can then have a go at working out part A. And so we have alpha plus beta would be equal to minus b over a, which would be minus 7 over 5, so 7/5. And alpha beta, that would be c over a, so that would be 1 over 5. Looking at part B, so we're working with the left hand side of this equation. We need to show that that is equal to 39 over 5. If we multiply that first fraction by alpha and the second one by beta, it will then have the same denominator. So that gives us alpha squared plus beta squared is over alpha beta. Now the numerator there, that is alpha plus beta all squared minus 2 alpha beta over alpha beta. Start substituting in those values then. So the sum of the roots is 7/5 squared minus 2 lots of the product of the roots, that's 1/5, and that's all over 1/5. And simplifying here then, we've got 49 over 25. 2 times 1/5, well that's 2/5. If I write that over 25 so that I can add that numerator together, that's times in by 5, that would be 10. So that's minus 10 over 25, and then we're dividing by 1/5. Working with that numerator, 49 take away 10, that's 39. So we'd be left with 39 over 25, and then dividing by 1/5 is the same as multiplying by 5. So we need to multiply our fraction here by 5, and that's going to reduce the denominator, and that will make that 39 over 5, just like we need. And so finally, looking at part C. So find a quadratic that has integer coefficients with roots alpha plus 1 over alpha and beta plus 1 over beta. If we start by finding the sum of the roots, so we'll start by adding those two together. And if I group together the things that I can work out, I know the value of alpha plus beta. So I just need to deal with that second part, that fraction 1 over alpha plus 1 over beta. So if I combine these into one single fraction, by multiplying the first fraction by beta and the second fraction by alpha, I will be left with alpha plus beta over alpha beta, which I can then substitute the values in from part A. And so we have 7/5 plus 7/5 divided by 1/5, which gives us 7/5 plus 7, which, putting into my calculator, gives me 42 over 5. So let's write the sum of the roots is 42 over 5. And then calculating the product of the roots, so we need to multiply these two brackets out. That gives us alpha beta plus alpha over beta plus beta over alpha plus 1 over alpha beta. And we can substitute in again, so we have the product, so that's 1/5. These middle two terms are the answer to part B, and so that would be plus 39/5. And then the final one, so we are adding on 1 over alpha beta, which is 1 divided by 5, so that would be 5. And so we would have 40 divided by 5 from these first two terms, which is 8, and 5 from the last term, and so this would give us 13. And we can then substitute our sum and product with these new roots to be x squared minus 42 over 5x plus 13. And finally, we just need to make sure we have integer coefficients there. So if we multiply everything through by 5, that will give us 5x squared minus 42x plus 65 equals 0. You might like to try this example for yourself before I go through the example. Pause the PowerPoint now and then I'll go through the answers. We have the coefficients A, B and C, so that's 4, 6 and 3. And for part A we need the sum of the roots, which is minus B over A, and the product of the roots is C over A, so alpha plus beta will be equal to minus 6 over 4, which is minus 3 over 2. And alpha beta, C over A, is 3 over 4. Part B, alpha squared plus beta squared is equal to alpha plus beta all squared minus 2 lots of alpha beta. The sum of the roots is minus 3 over 2 squared, and the product is 3 over 4. And working these out, that gives us 9 over 4 if we square that first one, and 6 over 4 for the second, which does indeed give us 3/4, like we are asked to show. And part C, so we need to work out the product of these roots and the sum of these roots. So starting with the sum there, if I gather together these two terms and take out a factor of 3, that gives me 3 lots of alpha plus beta. And the second lot of terms, if I factorise out the minus 1, that gives me another alpha plus beta. So that gives me 3 lots of alpha plus beta, that's minus 3 over 2. Take away another lot of minus 3 over 2. So that will give me minus 9 over 2 plus 3 over 2, which is minus 6 over 2, or minus 3. And the product of the roots, so we'll pop the sum is minus 3. And the product if we multiply these out, that gives us 9 alpha beta minus 3 alpha squared minus 3 beta squared plus alpha beta. And so gathering together, we have 10 alpha beta minus 3 lots of alpha squared plus beta squared, and we can substitute in the values that we know. So we have 10 lots of 3/4 minus 3 lots. Now alpha squared plus beta squared from part B is 3/4. And simplifying this gives us 30 over 4 minus 9 over 4, which is 21 over 4. Now we can substitute in our sum and product into the equation below. We've got x squared minus 3x plus 21 over 4 equals 0. Now we need integer coefficients, so I'm going to multiply everything by 4, but I'm also going to simplify this middle term here. So that will give me 4x squared plus 12x plus 21 equals 0. Let's take a look at an example for your notebook. So the quadratic equation 2x squared minus 5x plus 3 equals 0 has roots alpha and beta. And we need to find the value of alpha squared plus beta squared and use that to show alpha to the power 4 plus beta to the power 4 is 97 over 16. So let's start there. So using the quadratic that we are given, we can work out the values of the sum and the product of the roots. And we can then substitute these into the formula alpha squared plus beta squared. And this will give us 13 over 4. Now this is what we need to find, alpha to the power 4 plus beta to the power 4. And this is, if you compare the two, if you replace alpha with alpha squared and beta with beta squared, we will get this new formula. And we can then factorise out the squared on the last part of that expression, and we can substitute in those values that we know. So that will give us 97 over 16. And part B. So if we have a quadratic that has new roots for alpha to the power 4 plus 1 over beta squared, and for beta to the power 4 plus 1 over alpha squared, we need to find the sum of these roots. So notice that I've grouped together the alpha to the power 4 and beta to the power 4 at the front and the other two fractions at the back. So I can take out a factor of 4 here, and I've just grouped together just like the previous examples so that we have the same denominator, so that we can add those two fractions together. And then we can substitute in because we already know which each of these values are. And that gives us an answer of 925 over 36. Now the sum of these new roots will be minus b over a, so this is telling us what our values of a and b will be. And if we have a look at the product then, so multiplying out those two brackets, substituting in the values that we already know, this will lead to 850 over 9, and this will be the product of the new root. And so we use these just like we did previously, changing that second fraction so that it's over the same denominator. This helps us work out the values of a, b and c. And so we can then substitute those into the quadratic. Okay, so we have a cubic equation that can be written as ax cubed plus bx squared plus cx plus d, so the general equation. And when this is factorised, this could be written as three factor pairs with alpha, beta and gamma as its roots. Now we can use these equations to work out the sum of the roots, which is the first line there. This is the sum. We can work out the sum of the product pairs, and we can work out the product. So if we divide this first equation by a and set it equal to that second equation, just like we did when we were looking at quadratics, and multiplying out the right hand side, we can then gather this back together so we can start to compare the coefficients of the left hand side and the right hand side. So if we just take a look there, I'll try and underline in colour so that we can see where they're all coming from. So we have x squared here, here and here. So that leads to this first bracket. And we have all of the coefficients of the x here, here and here, which leads to the second bracket. And so if we use this, this will lead to the sum of the roots being equal to minus b over a. And in the box, this is the bit that you need to copy into your notebooks. The sum of the product pairs is equal to c over a, and the product of the roots is equal to minus d over a. And we can do this similarly for a quartic equation as well. And for your notebook, the sum of the roots is minus b over a. The sum of the product pairs is c over a. The sum of the triple products is minus d over a, and the product is e over a. For the next example, we need to find the value of 1 over p plus 1 over q plus 1 over r plus 1 over s for the equation written above. The first step is to combine those elements so there is one single fraction. And in order to do that, we need to multiply each fraction by all of the other denominators. So 1 over p we multiply by QRS. 1 over Q is multiplied by PRS, and that's when we multiply, we're multiplying by the top and the bottom, so it remains the same, just as you would do with any normal fraction. And then this would lead us to a fraction where the denominator is P, Q, R and S, and the numerators, we could write it all as one single fraction here, so the numerator would be QRS plus PRS, PQS and PQR. Now, referring back to the equation from the start, the coefficients here, so we have A is 2, B is minus 3, C would be the x squared term, so C is equal to 0, and we've got D is 1 and E is minus 5. Now, working backwards, we could work out P, Q, R, S, so that is the product of the roots, which would be E over A, and that is then minus 5 over 2. And the numerator is the product, the triple product sum. So QRS, PRS, PQS and PQR is equal to minus D over A, which would be minus 1 over 2. And therefore the fraction, if we go back to this top bit here, that would be minus a half divided by minus 5 over 2, which gives us 1/5. Now turn to page 42 and complete exercise 2D.